Welcome everyone to the next IIT seminar. So today we have William Campillay-Llanos from the Center for Advanced Studies of Fruticulture in Chile. And he's going to be talking to us about trophic dynamics and modeling biological control in trophic food chains, something I've worked in the past. So without further ado, I'm excited to hear what you have to say, William.
Thank you, Yuri. Good afternoon, everyone. Okay, you can hear me, okay? You can hear me?
Yes.
Perfect. Thank you for being here today. I'm currently postdoctoral researchers and Center of Advanced Study and Fruticulture in Chile. It is my pleasure to present my work to you and your audience. My collaborator for this project is Marlon Lopez, a mathematician based in Brazil. The primary goal of my current research is understand how body size influence the trophic dynamic with a three-level food chain. Through mathematical model, we aim to explore species abundance, energy requirements, trophic cascade effects, and the body mass condition necessary for species coexistence. I will start with a brief presentation of my work and its contribution to the field of theoretical ecology. Next, I will discuss the motivation behind my research. I introduce some key elements of mathematical modeling using in this study. I will then explore a three-level food chain focusing on how the body mass of predator, for example, specifically mountain lion, for example, affect the dynamic between rabbits and plants. Finally, I will examine another three-level food chain, this time considering the impact of biological control methods on pest population and plant health. Let's begin the first topic. I would like to highlight some of my professional engagement and collaboration. Firstly, I had the privilege of presenting my research at the Institute of Biology at the University of Talca. Additionally, I'm involved in teaching as professor biomathematical modeling at the Faculty of Agriculture Science at the University of Talca. I have also fortunate to collaborate with esteemed colleagues in my field. My collaborator include Dr. Samuel Ortega Farias, who was my postdoctoral supervisor at the Center of Researches and Transfer in Agriclimatology and Irrigation. Dr. Marlon Lopez, a mathematician, the postdoctoral fellowship for the Institute of the Pure and Applied Mathematics in Brazil. And Gonzalo Diaz, an agronomist, and Dr. Gonzalo Diaz, an agronomy and a specialist in phytopathology. Together, we are currently working on modeling a trophic chain that incorporates the body size of the insect. Also, we discuss a current research project with focusing on studying the effect of the pest on the watermelon with a trophic. Our research team is composed for several experts in different fields. Dr. Guillermo Toro, who is a specialist in plant physiology, Dr. Ariel Salvatierra, a specialist in genomics, and Álvaro Enriquez, a Master of Science in Applied Ecology. Together, we aim to understand how pest dynamics affect watermelon crop to develop an effective biological control strategy. Well, the motivation and some element for the mathematical model. This is the first idea. The first ecological pattern that caught my attention is the negative relation between body mass and population density. As shown in the figure, each point represents an species, and the x are the logarithm scale. This simple yet powerful relationship is known as the mood law, which has been used to predict the abundance, for example, T-Rex. Another straightforward yet significant relationship is the positive correlation between body size and metabolic rate, now Kleiber law. This pattern holds true for a wide range of the species. With this ecological information and basic mathematical technique, one can conduct scientific research and explore various hypotheses. This foundational principle has driven my interest and motivation in studying trophic dynamics and applied mathematical model to ecological questions. When we estimate the energy requirements of the organism and consider ecological pattern with an exponent 3/4, the allometric exponent 3/4, we find that by multiplying and using the property of the exponent, very simple, the energy requirement becomes independent of body size. This result for me is very interesting. This concept is proposed by researchers and Gismore and Damuth in 2008, is remarkable simply to present but challenging to explain. It reminded me of the elegance and complexity found in the Fermat theorem. This discovery has greatly motivated me and inspired me to explore ways to apply mathematics to ecological problems. It is open new way for me think about the mathematical model can help understand and predict ecological dynamics. Now I will discuss the recent study of Hayton and College in 2019. This study examined a large databases to investigate the relationship between basal metabolism, maximum growth rate, mortality rate, and abundance for a wide variety of these organisms. The author used this relation to uncover a scaling law that applied across different groups of the eukaryotes. In the study, organisms and color code for clarity. For example, red represent mammals, yellow represent protists, green represent plants, and blue represent ectotherms. This finding helped to further our understanding of how fundamental biological rates and abundance scale across different types of the organism provide a unified perspective on ecological and evolutionary patterns. We observe a positive correlation between metabolism and maximum growth rate with the body size. Large organisms tend to have higher metabolic rate and growth rate. Conversely, there is a negative correlation between mortality rate and abundance and body size. Smallest organisms typically have higher mortality rate and abundance compared to large organisms. It is particularly intriguing to focus on the abundance pattern. Inspired by this pattern, we embark on the process on the mathematical modeling, drawing inspiration from the ecological principle. By incorporating this ecological insight into our mathematical model, we aim to gain a deeper understanding of the underlying dynamics of ecological systems. Well, using the body mass abundance pattern, we construct three-level trophic food chain consisting of R resource, C consumer, and P predator. As abundance reach equilibrium, represented by a stable point, then we pose the crucial question: what happens if we disturb this equilibrium? And more importantly, how we can effectively shift this equilibrium? To address this question, we propose associating a dynamical system with this equilibrium point. This allows us to investigate the behavior of the trophic chain over time and understand the dynamic of the species. This concept is a core of the mathematical modeling, capturing the dynamic nature of the ecological system and exploring how change in one component affects the entire system. Well, additionally, we develop a framework for integration of the ecology and mathematics, collaborating with the Dr. Noemi Cárcamo, a specialist in teaching and mathematical modeling, with the article, How Do You Model What We Model? Well, look at this food chain. We now present a study that dynamical model this equilibrium state using three trophic food chain as an example. In this model, the mountain lion serves as the top predator, the rabbit as the primary consumer, and plant as the basis resource. By integrating from metabolic theory of the ecology, this is a food chain, this is a pattern, integrate the metabolic theory into the system of differential equation, we can dynamically analyze this equilibrium. This is a principal idea of my work. This approach enables us to explore species abundance, energy requirement, trophic cascade effects, and body mass condition necessary for the coexistence. To incorporate body size effectively, we draw upon the foundational work of Waite and Levin from 2006. Their study present and choose equation system and introduce a theoretical predation rate. This predation rate is particularly important at providing framework for understanding predator-prey interaction and more nuanced level. By applying this model, we can achieve close approximation of the ecological interaction, allowing us predict outcome with a great accuracy. The integration of the size parameters facilitates the derivation of several critical ecological results, such as species abundance, energy requirement, and effect of trophic cascade. One of the most significant advantages of this approach is that provide results that can be experimentally validated, bridging the gap between theoretical model and real-world ecology. I would like to emphasize the importance by incorporating the body mass into our analysis. Once we have established the body mass, we can determine the density and the metabolic rate is already defined by metabolic theory. Consequently, we can estimate the energy requirements by the multiply the metabolic rate and the species density. By incorporating body size into the system parameters, our study provides comprehensive insight into species coexistence, energy dynamics, and the conditions necessary for maintain ecological equilibrium. Well, the result of this work is we have calculated the equilibrium point for the basic resource and determine both lower and upper boundary for the species abundance. These bounds are crucial as they provide on range with which a species population can stabilize under given conditions. Our finding corresponding closely with significant empirical data. To the left, the result obtained for the model. This model illustrates the calculated equilibrium point and the bundle for the species abundance. On the right, we have an image from the Hayton et al. 2019, which provides a visual representation for the relationship between density and body mass. By comparing these two visuals, we can see the alignment between our model prediction and empirical data corresponding by Hayton and College. In this case, the energy requirements, based on this expression, we calculate the energy requirement for the predator and the consumer. We highlight the particular case when alpha is equal to quarter. We observe that the energy requirement of predator is independent of body mass, with the energy requirement for the consumer is bounded both on lower and upper end. Well, this result is related to Charnock finding on energy requirement. On the left side, we display the result from our model, while on the right side, we present empirical data from Charnock 2001 study. For study the trophic cascade, we utilize an idea proposed by Dillon and College in 2015. We suggest the trophic cascade are dependent on body size. Trophic cascade refers to the indirect effect of top predator on the basic resource through the consumption of the intermediate species. This dependence on body mass allows us to construct a three-dimensional representation to identify body size where the intensity of the trophic cascade is most pronounced. By incorporating body size into our understanding of trophic cascade, we gain valuable insight into the ecological dynamic of predator-prey interaction. This approach not only enhances our understanding of the ecosystem function, but also provides framework for predict the cascading effect of predator removal or addition in ecosystem. To obtain three-dimensional representation of trophic cascade intensity. This is a representation three-dimensional. For this, it's necessary to fix the body mass of the intermediate consumer. This allows us to generate the surface, and its control plot reveals, the control plot of this function reveals that the white area represents the combination of predator body mass and resource mass that generate the strongest cascade intensity. I think this information can be invaluable for decision-making when introducing a species into an ecosystem. By identifying the area of highest trophic cascade intensity, we can assess the potential impact of the introduce a new species on the existing ecosystem dynamic. Then this approach helps to inform management strategy or mitigate potential, for example, ecological disruption. To conclude, I would like to present a mathematical result from provide insight into a species coexistence dynamics. We solve in the differential equation and one calculate the coexistence point. In this case, this point exists for certain mathematical condition. Then which give rise on the following body size space. Look, see alpha equal 2/3, this is a corresponding to surface law. The body size piece is in the figure. If the alpha equal 3/4, representing Campillay law, the surface is further restricted. While finally, when alpha equal 1, this is an isometry, the surface is even more constrained. These findings have led us imagine that this relation can also be studied in trophic chain across different geological epochs. This such a mathematical principle governing species coexistence transcend temporal boundary, and the could potential provide insight into the ecological dynamic of ancient ecosystem. Well, the same idea, but now is another trophic trophic food chain. Now we have a control, we have a plant, we have a plant. In agriculture, combating pest control requires diverse strategy. In our approach, we propose the body size is a key trait ensuring effective biological control. We explore a three-level trophic chain, focusing on the dynamic between control organism, pest, and plant. By examining the interplay between this level, we aim to identify optimal strategy for biological pest control. Then our study underscores the importance of considering ecological dynamic, particularly body size, in agriculture management practice. We delve into our modeling of a trophic chain featured a predator density denoted by P, followed by the abundant pest represented by C. And the plant we aim to protect, label the abundant as R. In this study, we have incorporated the holding type 2 functional response, wherein the predation rate saturates as the prey abundance increasing. This ecological concept highlights how predators adjust their feeding rate based on prey availability, influencing the dynamic and the entire ecosystem. Through our modeling approach, we aim to explore various properties of this dynamic system. By understanding the interplay between predator, pest, and plant dynamics, we can gain valuable insight into ecosystem stability and the efficacy of pest control strategy. This is a first theorem. To establish the ecological realism of the system, it is crucial to verify that solutions are non-negative and bounded. This condition depends on body size and is proportionally to the current capacity on the basic resource. The surface observed represents this condition. This is a surface of this condition. It is important to note that the condition serves as a bottom-up constraint, ensuring the coherence of the mathematical representation of the ecological system. By imposing this constraint, we guarantee that the model reflects or represents the ecological reality. In the same system, we have obtained a threshold parameter denoted by R0. R0, using the state-of-the-art metrics technique, I do not delve into mathematical detail to add depth to ecological results. It is important to understand the ecological implications. Look at, if the R0 is less than 1, both control and pest species go extinct. However, if R0 is greater than 1, both species persist. Of particular interest of us is the scenario where R0 is greater than 1. In this case, we ask ourselves, at what body size does this occur? What body size does this occur? This ecological question where mathematics can provide valuable insight. To address this question, we consider R0 as the function of two variables and obtain its graph and contour map. This is a function in the left side. This is a function in two variables. In the right side, this is a map contour. By visualizing the relation between body size and R0, we can identify the ecological condition under the pest control is effective and the pest population persists. This is a quantitative result for control pest. Well, in the sizing system, I will explain another R0 obtained on the threshold over the sizing system. By fixing of the mass of biological control, they obtain the threshold indicate that if R0 is less than 1, the control species go extinct. This information can be valuable when evaluating the introduction of certain species for pest control. On the other hand, if the R0 is greater than 1, the control species persist. Well, when fixing the mass of the control species, R0 allows us to obtain a function and two variables and corresponding contour and it is corresponding contour map. Then this is our R0, fixing the mass of the control species. Then in the side and the left side, we have the function and variable. In the right side, we have the map contour. Then the conclusion, darker region on the contour map indicate the R0 is greater than 1. This insight helps us identify the ecological condition under which the introduced control species can effectively manage the pest population. Another phenomenon that I can study in the system is the phenomenon of trophic cascade. The same idea. The idea is the DeLong and colleagues. This is an article in 1950. This approach enabled to us to identify the trophic cascade, which is dependent on body size. By utilizing this framework, we can identify the relation between body mass, where they affect the biological control and target plant intensify. Starting from the surface obtained, this is a function. we can generate a graph of an control line. Look at darker region on this contour, indicate areas where the trophic cascade intensity is higher. This insight helps us understand the ecological condition based on body mass, where the impact of biological control on the target plant is most pronounced. This is a final result of our research. This is model trophic cascade. Is now I'll show you a new job that worked with this is our team is interested in determine the chaotic behavior of the system. We can construct surface. This is the idea. We can construct surface and body mass space for which chaotic dynamic occur. This work is deeply inspired by the research and McCann and Justin, 1994, author who I personally may not acquaint with, but who have profoundly influencing our work, our study, really. This research has provided invaluable insight guiding our exploration of a chaotic dynamic within our ecological system. Lastly, another projection involved collaboration with the Center for Advanced Study in Fruticulture. We aim to incorporate theoretical study on trophic chain in central southern region of Chile. The trophic cascade, the really trophic cascade, is with this insect. This is a future job, future challenge. We are confident that this modular approach can provide answers applicable to biological control strategy. By integrating theoretical insight with practical application, we aim to enhance pest management and ecological conservation efforts in the region. Well, to conclude, I'd like to share primary reference used in this presentation. I had the opportunity of read the book Theory-Based Ecology, a Darwin Approach. I like a lot this book. I like. Finally, I want to express my sincere gratitude for your time and kindness in listening to me. Thank you, Yori.
Thank you very much, William. And thank you, everybody, for being here. Now, if you have questions, let me know by raising your hand in the chat as usual, and I shall call on you. So, any questions? First of all, two small technical points, then something bigger. Sorry. So one of the technical points was you were showing your R naught, and it was just written in a weird way, and I wasn't able to figure it out. So if you go back a few slides, a bit more.
Which figure?
Yeah, exactly. That's the one. So this R naught P. Why is it a function of MR twice? Or is that just a typo? So it's this R naught is a function of MR, MC, and then MR again.
Excuse me.
Am I making sense? Yeah, that's good too.
Okay. Repeat, please, the question, please.
My bad. Can you go forward two slides or back to where we were just a moment ago.
You tell me.
No, it was where you had the R naught P. Where
P?
you were calculating that R naught. It was in point 4, so it's a bit forward from this point. So if you go forward, not backwards, forwards.
Ah, forward. Okay, thank you.
Forward, yes. A bit more.
Yeah. Okay. That's good.
This, yeah, okay.
So what I don't understand R naught P. Why is it a function of MR twice? Right? It has 3 arguments. But I think
What
you
is
said,
that?
sorry.
Repeat, please.
Yes.
I'm sorry. May I help? Is that I worked with I'm Marlon Lopez. I'm co-author of that work, and probably he's not understanding your question. I'm going to speak in Spanish so he understands. William, él está preguntando por qué tiene 2 veces MR en la expresión, que probablemente es un typo, que debería ser en vez de ser MRMC, MP en el final. O sea, eso es lo que él está preguntando.
Ya, perfecto. Pero en el gráfico, en the graph, on the
No,
expression.
no. En la expresión, él está preguntando que por qué está 2 veces MR. Entonces probablemente es MP que está ahí. Ese sería un typo, ¿verdad?
Yeah.
Actually, this is a typo. Yeah,
Okay.
because it should be MR, MC, MP.
Okay, so it's 3 yes, okay. I was
Yes,
confused because I thought during the talk it was mentioned that this is a function of 2 variables, but maybe that was just it's 3.
Yes, 3 variable. Yeah.
Okay.
R, MC, and MP. This is my mistake.
No
Because
worries. That was technical small point number 1. Technical small point number 2. Can you go backwards a few slides where you introduce R naught? There we go. Yeah, forward 1 or backward. There, in the last point, you say CT plus PT persist. Is that to be interpreted that at least one of them persist or both of them definitely persist? So in your final bullet point, where you say if R not larger than 1, then C plus P persists uniformly.
Okay.
Is that C plus P or C times P? In that do you mean that at least one of them will persist? At least the consumer will, at least one of those, well, at least C will, I'm forgetting which one is which, but then anyway, at least one of them, the lower level, will persist, or both of them definitely persist.
May I intervene?
I'm very grateful if you can play translate.
Sure. Él está preguntando que si el CT y el PT en conjunto ellos dos persisten o es uno de ellos que el que persiste.
Sí, yeah. Because PT is maybe equal 0. It persists and C in the mathematical result for us is the summa, the addition persists.
So it's also almost like a logical or that at least C persists, but maybe P. Okay. Thank you. That's one that was good to clarify. So that doesn't mean that the system as a whole persists, just that at least all the levels. And then I guess I had some broader points, which is in the beginning of the talk, you were writing a model which had a type 1 functional response at the start. Well, yeah, exactly. And then you were analyzing the stability of the equilibrium point in this system.
Mm-hmm.
But is the equilibrium point actually stable? I mean, these systems tend to oscillate quite a
No,
bit.
not oscillate. This is
Oh,
not
it
stable.
doesn't. Okay.
Doesn't.
It is a stable fixed point.
Yeah.
Okay. Is that because of the logistic term in the...
No, but in this system is the functional response one. Then it's a similar local Volterra system. It's similar.
Yeah, exactly. So those tend to generate oscillations. So that's why I'm wondering. I'm not quite certain because in the resource equation you have a logistic growth term, and that tends to stabilize the dynamics. But what maybe somebody else in the audience knows off the top of their head. But maybe you know, William, when did you actually analyze the stability of the fixed point, or
Okay,
just the
in
position of the fixed point?
the fixed point, the equilibrium point for this model is represented with this figure. We have four equilibrium point.
And the arrows are pointing in the direction of the flow.
Yeah. Yeah.
Oh, okay, so it is stable.
This is stable.
Okay, this is stable. Okay, thank you. Okay, so this does not keep oscillating.
And in the very good question, because when you change the functional response, look at in this case, in this system, there are oscillations.
Oh, okay.
Yes.
There are oscillation, and also there are, because this system is have a chaotic dynamic, because the structure of this system is similar, and McCann and Peter just this work. Then with holding tight two functional response, there are oscillations. Okay, and even chaos.
Okay. Oh, okay.
Yeah.
Thank you. Thank you so much. Yes. So, are there other questions? Questions? Thank you again, William, for the talk, and thank you for coming, and thank you everybody for coming. This is actually, I believe, our last IIT seminar for the term, so we will be in touch, and we will be planning to resume next fall. So hope to see you all then. So until then, have a great summer. So thank you everyone, and see you next
Thank you,
time.
George.
Thank you. Bye.
Bye-bye.
Thank you.